Okay, we're going to look at a graph theory analysis with an adjacency matrix. So this is a worked example, and the point is really to test our ability with graph properties, specifically connectivity and completeness, and the existence of Euler trails, Euler circuits, Hamiltonian paths, and Hamiltonian cycles. Okay, so part A, there's two parts of this. So given the graph G with the vertices 1, 2, 3, 4, 5, and 6, draw the graph with the following adjacency matrix. Okay, let's just take a moment to study that and just see if we pick up any patterns there. So let's look and see what vertex 1 is connected to. So vertex 1, which is the top row, not including the column headers, is 0, 1, 0, 1, 0, 1. So it's connected to 2, 4, and 6. Let's look at number vertex 2, 1, 0, 1, 0, 1, 0. So it's connected to vertex 1, vertex 3, and vertex 5, and so on. So what you'll sort of see here is that basically the vertices with even numbers are connected to all of the odd numbered vertices, and vice versa, all of the odd numbered vertices are connected to all the even numbered vertices. Okay, that's important. Is the graph connected? Is the graph complete? Well, we'll come to that shortly. So the part B is, does the graph have an Euler trail? Does it have an Euler circuit? Does it have a Hamiltonian path? Does it have a Hamiltonian trail cycle? Okay, so that's just, we'll come back to that one shortly, part B, but let's just go back to part A now. So we have all of the questions there. So vertex 1 is connected to vertices 2, 4, and 6. Vertex 2 is connected to 1, 3, and 5. Vertex 3 is connected to 2, 4, and 6, and so on there. And you notice that pattern very quickly about that all of the even number vertices are connected to all the odd number vertices, and all of the odd number vertices, and vice versa, all of the odd number vertices are connected to all the even numbered vertices 2, 4, and 6. Okay, that's important later on. Okay, but so far that's what we have there. That's just a restatement of the adjacency matrix up above. So I think I really covered everything there. So just to remark, this is a complete bipartite graph and is denoted K33. Now that's not really part of the question. This graph is connected since each vertex in 1, 3, 5 is connected to each vertex in 2, 4, 6. So there is a path between each pair of vertices in the graph. Okay, so not really important yet. Well, that bit is important. Just as a quick remark, this is what we would get if we sketched it out. This is one possible representation, although you would traditionally put a bipartite graph in a very structured format with all the even numbers on one side and all the odd numbers on the other. But it doesn't really make a whole we were going to use the graph or the matrices anyway, so it doesn't make a lot of difference. But that's using an R package called iGraph. There are a couple of computer programming packages that you can use to create these graphs. They're very interesting. I won't get into that now because it'll take up a lot of time. So moving on to the next part about connectedness and completeness of the graph. Exercise 2 of part A. Is the graph connected? Yes, the graph is connected because there is a path between any pair of vertices. Okay. Exercise 3, is the graph complete? And remember, it's complete, not bipartite complete. So just is it complete? Straightforward question. No, the graph is not complete because not every pair of vertices is connected by an edge. In a complete graph with 6 vertices, every vertex should be connected to every other vertex. Okay, and that's not the case here. There are quite a lot of zeros in the adjacency matrix. Okay, so moving on to part B. So we have 4 little exercises here, 4 little questions. And essentially what we're doing here is checking for Euler and Hamiltonian properties, or the Eulerian if you want. Does the graph have an Euler trail? So what does that mean? An Euler trail exists if and only if exactly 2 vertices have an odd degree number of edges. Okay, so here each vertex has a degree of 3, which is an odd degree. Okay, so if you just go through it again, I'll actually just scroll back there very quickly. Just down there at the bottom, each vertex is connected to 3 other vertices. Okay, so that's a no. Okay, oh good, there we are. So here each vertex has a degree of 3, odd degree. Since we have more than two vertices with an odd degree, the graph does not have an Eulerian trail, an Euler trail. Does the graph have an Euler circuit? Well, an Euler circuit exists if and only if all of the vertices have an even degree, and in this case, that's not the case because they all have an odd degree. So there's no Euler circuit. So 3 and 4, Hamiltonian properties. Does the graph have a Hamiltonian path? Well, a Hamiltonian path is a path that exists, that it visits each vertex only once. Okay, so given the symmetry and the connectivity of the graph, there is a Hamiltonian path. For example, one such path would be 1, 2, 3, 4, 5, 6. Now, you remember what I said actually earlier on, because this is relevant here. I said earlier on that each vertex, each odd number vertex is connected to each of the even number vertices, and vice versa. Okay, that's important. So you can go to start with an odd number, then go to an even number, back to an odd number, a different odd number, go to a different even number, go back to a different odd number, and then go back to a different even number. Okay, and that's one example there. So that's a sort of possible outcome there, and that's why this is a sort of importance, why I mentioned it earlier on. Okay, so hopefully that's clear. Anyway, does the graph have a Hamiltonian cycle? Okay, a Hamiltonian cycle is a cycle that exists, that visits each vertex exactly once and returns to the starting vertex. So yes, this does have a Hamiltonian cycle, just sort of referring back to exercise 3. One such example would be 1, 2, 3, 4, 5, 6, 1. Okay, so when you're at 6, you can go back to 1 once you've visited all of the other vertices. Okay, and that's it. We'll leave it there. Okay, bye-bye.